Get this on the record. Here we go. So assignment number 2 is due on Monday, whatever that date is, 27th. Time flies when you're having fun. So at midnight, of course, at 11:59. Okay. So it was due tonight. I'll give you guys the weekend to worry about it. How nice of me. Oh, I should do that. Oh, I should do that. Now, if you've done it, that's great. We finished all the material that you need, right, on Monday. So you have everything that you need. Some of the questions, right, so just keep in mind that assignments, they're meant to like stretch your brain a little bit, right? They're gonna be harder than something I would expect on a test, right? So because you have resources, you can ask me questions, you can talk to each other, you've got time, right? And so all these things, the assignments, they're not worth very much, right? And so that's my opportunity to kind of be like, oh, here's another thing we could think about, right? Thinking about how the mean behaves, for example, right? Just things like that. Okay. I'll also make a note, but from now on, the labs that we do will just be due the following week on the Friday at midnight. Right? So lab 2 is due this Friday, January 24th at 11:59. I didn't hear any complaints about not having a lab on January 31st using one of our spare labs. So no lab on January 31st. Cool? Cool beans. No lab on January 31st. Right, because remember we have some spare labs, because this term we actually get more lab times than in the previous term, but we make material for the shorter term, so now we've got a little bit of wiggle room here. So no lab on January 31st. Okay. All right. Housekeeping, done. We finished chapter 2. Saying goodbye to that. No, not really. He'll come back. But today we'll start regression. Regression is kind of the start of actual statistics that we're going to do, right? And so we're kind of starting off slow. I say regression, but you've probably done some sort of line of best fit, right? You've plotted some data, you've drawn a line of best fit at some point. I remember in high school, I think it was in chemistry or something, we had this plot that we'd made by hand for some reason. And then we just said, oh, here's the line of best fit, and we just drew it. It's a little bit more sophisticated than that. And so in this chapter, we're going to develop the formulas for figuring out what the line of best fit is and talk about what it is. But so chapter 3. Oops. Chapter 3 is on simple regression. So you've probably seen a scatter plot, right? And so we'll talk about scatter plots in a little bit here. But the reason that we do regression is because we've got some research question, right? does an increase in this affect the outcome of this, right? So we've got some research question. And so the variable that we're interested in is going to be our response variable. All the other variables, and we can have more than one, would be explanatory variables, right? And so they're trying to explain changes in the response variable. Okay? And so in a research question, the variable of interest is the response variable and any other variable, and then I'll put in bracket S because we could have more than one, and any other variables will be considered explanatory variables. Will be considered explanatory variables. In simple regression, we're only going to have one explanatory variable, right? So that's why we call it simple, is because there's only one explanatory variable. So in simple regression, we will only have one explanatory variable. So in section 3.1, just talks briefly about scatter plots. So scatter plots, we're analyzing the relationship between two typically numerical variables, okay? Especially for us in this course. And so we want to be able to visualize that relationship. Okay? So we use scatter plots to visualize the relationship between two variables, right? Typically numerical. Between two variables, and then I'll put in brackets here, typically numerical. For us, we're going to focus on numerical variables. So a scatter plot, right, is going to look something like this. We've got kind of our x-axis and our y-axis. And then our points, right, if we've got a spreadsheet of data and I've got a x column and a y column, right, I've got these pairwise observations, right? Person number one, I measured x and I measured y, right? I measured their height and I measured their weight. So those would be paired, right? And so now we're able to plot those as paired coordinates. So here, if we have this kind of relationship, something like that, that'll be my go-to scatter plot. Just kind of any old scatter plot. But what we do is we put the response variable on the y-axis. Okay? So the response goes on the y-axis, And the explanatory variable goes on the x-axis. And that's why I like to use explanatory, because it has the x in there, so you can remind yourself that the x goes on the x-axis. So explanatory here. Explanatory. Yeah. And then I did have one student a long time ago who said she had a hard time remembering which was the x and which was the y-axis. But then she just imagined this little guy on the bottom, the x-axis, going, no. So whatever you got to do, right? And so I think that's really cute. So now whenever I write the x-axis, I'm like, no, because the other one can fall on it. So pretty cute. So whatever you got to do. All right. So if we drew a line of best fit, just a line of best fit, let's go and draw it just kind of through here. This is our line of best fit. Which is our linear regression. We have to think about why we would even want a line of best fit, right? The line of best fit is, so we've collected this sample data, right? But remember, our whole goal is to be able to talk about the whole population. How would the population behave, right? And so this line of best fit is trying to model what the population would behave like, right? And so what we use this line for, typically, is to predict values that we haven't seen in our data, right? And so now, based off of our data, we're able to say, well, I know the population should behave like this line, right? And so that means I'm able to predict future values, right? And so we use regression, right? And that's going to be maybe a little bit of a change, right? When I say regression, I actually mean line of best fit or fitting the line of best fit, right? So we use regression to model the behavior of the population, the behavior of the population and we use that model, right, to predict new values. And we use that model to predict new values. New or future, or however you want to think about it. So remember how when we looked at the histogram, we had to talk about 3 things to fully describe this distribution, right? We had to look at the shape. Was it a normal distribution or something non-normal, right? We kind of classified it as normal or non-normal. We had to look at the center. So where are most of these things happening? And we had to look at the spread, right? How much variation am I expecting to see here, right? What would be weird? And so when we're looking at a scatter plot, there's 3 new things we have to think about, right, to fully describe this relationship. One of which is, I'll call it the shape again, right? But by the shape, I mean the pattern, right? I just like to have the same, at least a little bit of overlap, right? And so here, if you have to describe this pattern, it looks like a straight line, right? And so we would say that this is a linear relationship, right? So a straight line, linear regression, we're fitting straight lines, right? So it's all snowballed in, right? A nonlinear regression would be something where maybe it shoots up like this. Maybe it starts down here low and then all the points just kind of woo, right? That can happen, especially if we're modeling things like population growth, right? Then we've got this nonlinear relationship, right? But just like we did with normal, either it's normal and that's what we care about, or it's non-normal and we're just going to leave that for a different stats course, right? Again, it's linear. We're going to know how to deal with a linear relationship, or it's non-linear. We'll parking lot that for a different stats course, right? And so, because that's a little bit, ugh, okay? And so, but to let you in on the secret, we just manipulate it until we have a straight line, usually. And then we're like, oh, I know how to deal with a straight line. So that's why we start with the straight lines and go further later, okay? So, when describing the relationship between two variables, right? The scatter plot is visualizing the relationship between two variables. And so essentially what I mean here is when describing the scatter plot, right? So when describing the relationship between two variables, right? And I'll put in brackets the scatter plot. We need to discuss three things. We need to discuss three things. First of which is, I'll call it the shape or the form or the pattern. But just to have the same shape center spread that we had for the histogram, right? So now I'll call it the shape, but you can think of it as the pattern or the form. But essentially, we're going to break it down to linear versus nonlinear. Linear relationships, something like this, where it looks like our best option for describing this pattern would be a straight line. Right? Or nonlinear, well, is anything where if you fit a straight line to it, it wouldn't really help you describe this relationship, right? And so you can have something like we talked about, kind of population growth here. Right? That would be nonlinear because you've got this curvature. Right? You can have all kinds of weird patterns going on, right? But that's a pretty common one. Okay. The problem here, right, as we can see, is that, yeah, if I try to fit a straight line to this, that's doing a pretty good job, right? If I try to fit a straight line through here, well, it's doing a pretty good job down here and here where it kind of processes through the data, but a terrible job of modeling that relationship everywhere else, right? And so that's why we need to figure out, well, what else can we do here? But for us in this course, we're focusing on linear models. Right? And so one of the assumptions, in fact, the main assumption that we need to check before we fit a model, right, before we do the regression, is do we have a linear relationship, right? And so the reason for that is if I fit a straight line to a curve, it doesn't really do anything. Right? So that's what the first thing you have to check is, do we have a linear relationship? The second thing we have to check is the direction of this relationship, right? So now we're assuming that we have a linear relationship and the direction can be either positive or negative. So again, I'll draw a little. My go-to relationship is a linear positive relationship, kind of up and up. They're both increasing together. And a negative relationship is going the other way. So we need to be able to see if we have a positive or a negative relationship. The last thing we need to talk about is the strength of the relationship. The strength of the relationship, I'm going to just classify it as either weak or strong. And we can go through and have different cutoffs, right? We could say moderately strong, moderately weak, very strong, right? Depending on what we're looking at. And so what we can have is a weak versus a strong relationship. A weak relationship would look something like this, kind of a big cloud. Right. If you kind of squinted hard enough, you could probably say that, oh, there is some sort of pattern in there, but not really, right? And so what I want you to look at, hey, where's that meter stick? Right, so what I want you to look at here in this cloud, should have made my dots bigger, but hopefully you can see them. If I'm fitting my line of best fit in this cloud, it actually doesn't really seem to matter where my line goes, right? Making my predictions not very reliable, right? Because, I mean, we have methods for fitting this line, but if we have a weak relationship, then our predictions they can't be very good, right? Because there's no real pattern in there. Whereas the ones that I've been drawing, they've all been strong relationships because we can see this obvious pattern. Where they all kind of behave the same. So here, it's obvious where this line should go, right? As a rule, I would say if you look at a scatter plot and you see a pattern, we can say it's strong, right? And so as soon as you see a pattern, it's strong. You could say it's moderately strong if it's not, very distinct. But don't worry, we'll have numerical measures of the strength in a little bit, so don't worry. But all right, so to describe the scatter plot that we kind of made up earlier, right? This is a strong, positive, linear relationship. So you have to talk about all three things. The order doesn't matter, of course. Just do what kind of sounds nice to you, but you have to touch on all three things. Bless you. So our first scatter plot can be described as a strong, positive, linear relationship. So, any questions? Oh. Not really. So it's good. You got me. No, the reason, because for a weak relationship, right, the problem is that, well, we would probably default to a line because it's the easiest. But I mean, if you've got something that looks like, and I'll just sketch this out here so it's big. If you've got something that's just kind of random scatter, like this, well, one, there's no association, so we probably wouldn't model this. We could fit a straight line through. We could do something weird like model it like this, right? So we could do something like this. I don't know, right? And so we have lots of options, but our predictions are not going to be very good anyways because we've got this weak relationship that we're dealing. So, yeah. Maybe something like this. Maybe. That's all right. But we'll talk about, because we've got that cluster in the bottom, right? So we'll talk about, those would all be considered outliers. And so we'll kind of talk about what we should do in those situations. If you see something like this, you can go ahead and you can model it the way it is, right? To me, it looks like there might be two groups that should be modeled independently, right? And so, so then you would kind of zoom in on here, right? And then zoom in on here. Here, there's obviously a linear relationship. It's possible that there's no relationship in these guys individually. And so, really good questions, guys. Yeah, so that, if there's kind of distinct groupings, we typically just divide them into groups that we think might be going on. Cool. All right. I am going to remove these so they don't take up half a page. Okay. 3.2. Here we're just going to talk about just the basics of linear regression, right? What is a straight line, for example? And so here we're talking about the basics of linear regression. If I say y equals mx plus b, kind of perk up a little bit. Yeah, that sounds familiar. You may or may not remember that that's the equation for a straight line, right? And so in math, right, we use y equals mx plus b as the equation, I guess I should say we use y equals mx plus b as the equation for a straight line. Oops. The equation for a straight line. Okay. We've got a couple of different things going on here, right? Remember, m is the slope. And I want you to remember it as just being the thing that's attached to the x, right? So you've got the slope, and the b is your y-intercept. So where this line crosses the y-axis. The two new things that we're adding in, right, is the x is now going to be our explanatory variable, right? Because that's what we put on our x-axis. So it's the value of the explanatory variable. Explanatory variable. And the y, right, that's going to be your response variable, because that's what we put on the y-axis. So we knew the slope and the intercept from before, right? But now instead of just y and x, we need to start thinking about, well, x is actually the value of my explanatory variable, and y is actually the value of my response variable. And so remember, the whole idea of making this line of best fit, of doing the regression, was to model the relationship in the population, right? Just like we had before, where we had maybe a sample mean to try to model a population mean. Now we're going to have a sample line to try to model a population line, right? And so in statistics, we will try to model the relationship between the response and explanatory variable, the relationship between the response and the explanatory variable in the population. In the population. So the general setup of our straight line, it's not going to change. We're still talking about a straight line, but now for our population, we're going to use Greek letters for our slope and our intercept. And so we use betas. And so beta, capital beta, is a fancy B with a long tail, right? And we put a subscript 0. Oh, made my, you know what? I like my old 0 there. Beta naught is how we usually, right? Beta 0, beta naught, meaning null, 0, nothing, right? And so beta naught plus beta 1 times x. If you spend a little bit of time, you'll be able to convince yourself that yes, this does have the same setup, right? I've got beta 1 attached to the x, so beta 1 must be the slope for the population. Beta naught is on its own, so it must be the y-intercept for the population. So here, this is the y-intercept for the population. And beta 1, oops, is the slope for the population. We're not going to know what beta naught and beta 1 are, right? But they're what we're trying to figure out what they are, right? Or what they might be. And so just like we said, okay, well, if I want to know what mu is, remember mu is the population mean, then I'm going to take the sample mean, and that's going to be my best guess, right? I take a sample, and that I can calculate the mean of, and then that's my best guess for the population mean. And so we estimate the parameters. We estimate the parameters using data, and we find, remembering that parameters is everything that describes the population, right? So those betas are parameters. So using data now, we find that y with a hat on it, so just a little hat, we'll talk about that in a little second here. Y hat, I'll make a nicer hat though, there. Y hat is b sub 0 plus b1 times x, right? Just using lowercase b's to denote that, oh, b naught is estimating beta naught, right? B1 is estimating beta 1. Right? All right. The new player is the y hat. Remember how we said anything with a bar over it just means it's a sample average? So now, when we're talking about regression, the hat is saying this is a predicted value, right? So this is my best guess given the data that I have, right? And so y hat is the predicted value of y. Remember, the whole goal of this was to be able to predict new values of the response variable, which is y, right? And so we're trying to figure out y hats. Okay. So this is the estimate of beta naught, and B1 is the estimate, bless you, of beta 1. Just a heads up that on the formula sheet, the formula is reversed a little bit. And so on the formula sheet, and if anyone needs, if anyone didn't get one yet, I've got some here. On the formula sheet, it's written as y hat equals b1x plus b naught. So just reversing those guys a little bit. Now, I don't know if that's to make it match y equals mx plus b, right? Slope times x plus the intercept. I'm going to think of it as later on, we'll see when we calculate the slope and the intercept, which is what we'll be doing, we have to find the slope before we can find the intercept. So for me, this serves as a reminder to say, okay, well, I have to first find the slope here, right? Even though if we're looking at the subscripts, it looks like the intercept comes first, but it doesn't. Okay. So, but those are the same. We're allowed to rearrange when we're adding. Okay. Cool. Any questions? Oh. So we're going to put that to the side a little bit and just talk about how we get this line of best fit. Very kind of theory heavy. But section 3.3 is called line fitting and correlation. I'm going to make a note again, right, that it's really important that we're only talking about linear relationships here, right? And so for this chapter, definitely only linear relationships. And so it is important to remember that we are only considering, oops, linear relationships in this chapter. So we're going to talk about the method that we use to find the line of best fit. How do we even define, well, this is the line of best fit, right? I can draw a line any way I want, right? But how do we determine which is the best line? We use what's called the least squares regression line. And so it's a little bit like you're chasing your own tail, because what happens in the background is, of course, your computer does this. You don't have to do this, not anymore, maybe like 100 years ago, but now our computer does this in the background, but we have to know where it came from. So what it does is we give it some data, right? We give it a scatter plot essentially, and it fits a line. And what it does is it calculates the difference between the line, right, that it's trying to draw and all the points, right? So that distance between a point, so an actual data point, and the line is what we call a residual, right? It's a leftover from the line to the actual data. Okay. So if we have data, and we fit a line to it, the distance from each point in the data to that line, from each point in the data to that line, is called the residual. Is called the residual, or I'll put in brackets, or error term. I just prefer to call it residual. You can call it error or residual. Error just has such a negative connotation, right? It's bad. So residual, it's just the leftovers. But it's going to be denoted by a lowercase e. So each data point is going to have a residual. And so what we say is that, okay, well, e subscript I, this is just saying the residual for the ith observation. Okay. This is the residual for the ith, so any observation, right? Ith observation. I know things got mathy real quick here. The residual for the ith observation is yi. So that's your actual y value in your data. or I'll say observed y value in the data. Minus, remember on that line, that whole line was for y hat, right? The predicted values of y, they're all lined up on that. The predicted values of y are all lined up on the line. Ugh, sounds weird. But so what we say minus y hat or yi hat. Right? And so this is the predicted value of y for the ith observation. I'll add to the yi, I should have said observed y value in the data for the ith observation. Okay. So your residual then, if you have to think about it, we can say is the observed minus the predicted. Right, if you want to summarize it that way, that's fine. On your formula sheet, they've got the observed y minus the predicted y, kind of meeting halfway. Or the residual is the observed y minus the predicted y. And that's the one that's on your formula sheet. So what does this look like, right? Well, we said, okay, so I've got this x-axis, I've got this y-axis, and I've got my data. And now I'm or in the background, the software is fiddling around and trying to fit a line, and it decides on a line like this. Each of these points has its own residual, right? Because it has its own point, and we can find the corresponding point for that value of x. I'll just highlight some points here that we're going to look at. These 3 points that I made kind of stronger. From this value of x, right, at the same, oops, at the same value of x, for each of these, now it's going to be a little bit tricky here. Trying to kind of, that one's a little bit curved, but it's okay. Can kind of, oh, it's hard to see, I guess. Something like that. My lines are straight. So, let me just check. I felt like there's a, no, and I'm not on mute. I thought there was a notification, and usually if there's a notification, I'm on mute, and that's bad news. So I think we're okay. All right, so we've got each of these observed values of y, right? If we focus on the one in the left-hand corner here, right, at that value of x, I can map over to the observed y. So the observed value of y. But also, on the line, I can map over at that value of x, and that would be my predicted y. And the distance between these two, I should have done a wider one. I'll do this one. How about? This distance is the residual. All right. So we need these residuals, and the residuals tell us a lot about how the line fits. But we also use the residuals to fit the line, so it gets a little bit weird, right? But to find the line of best fit, the method that we're going to use is the least squares regression line. And the least squares regression line says, I'm going to compute a bunch of different models, and I'm going to find the line that minimizes, so making the distance the smallest, right, that minimizes the square of the residuals. Okay, so we don't need to talk about why that is, but that is what we're doing, right? So it's looking at all these distances, and it's squaring all these residuals. Remember when you square a value, even if it's negative, right? If you did observed minus predicted here, this observed value is less than the predicted value, so you would end up with a negative value, right? So all the values below the line give you negative residuals. All the values above give you positive residuals. But if you square a negative value, right, it's positive, right? So it turns positive. And so what we do, right, is we use the square of the residuals, and we try to minimize that. We try to minimize the squared residuals. And so we find the line of best fit. So we find the line of best fit by minimizing the sum of the squared residuals. Okay. So we pick the line, yeah, sorry. So the squared residuals look like this. So E1 squared plus E2 squared plus E3 squared, right? So all these residuals, we square them, and then we add them all up. Let's say En, that's our sample size, squared. And then we minimize this value. So we square all the residuals, because if you're adding a positive value and a negative value that are about the same, then you end up at 0, right? And so that's why we square them, so that we can deal with just positive values on the same scale. Right? Another reason that is not important, but often a large residual, right, is more than twice as bad. So if we square a large number, it becomes really, really large. If we square a small number, it just kind of stays within the normal realm. So it magnifies these bad residuals. But anyways, that's neither, well, it's fun to know, I guess. So when we say regression, right, we actually mean least squares regression. Because that's the method that we use. But that is the most widely used. I don't see why you would use anything else. But when we say regression, we actually mean least squares regression. Least squares regression. least squares because it's minimizing the square root of the residuals. So we use the residuals to try to figure out what the line of best fit is, and we use that as a criteria. Well, whatever line minimizes the distance essentially to all these residuals, that's the one we're going to use. We also use the residuals to try to look at how the model fits the data. And so we also use residuals. We also use residuals to assess how well our model fits the data. So how we do that is through residual plots. And so a residual plot is a plot of the residuals as the response, right? So that puts it on the y-axis, right? Our response variable goes on the y-axis. And the explanatory variable stays on the x-axis. And the explanatory variable on the x-axis. Right. The residual plot, the reason we use them is not obvious when you first look at a residual plot. It'll look like the scatter plot, but just kind of tilted, so the line is straight across at 0. But the reason we use them is because it magnifies how the dots are behaving around the line, right? And so we use residual plots. We use residual plots because they magnify how the points are behaving around the line in the scatter plot, are behaving around the line in the scatter plot. For example, if we look at a slightly nonlinear relationship, so here's our response, and here's our explanatory variable, whatever it is. And we have this kind of, let's see if I can draw just a slight curve here. It would probably try to fit the line something like this. Right. It's under predicting for the first part, and then it's over predicting for a good chunk of the x's, and then it's under predicting again, so it's not really doing a very good job. Kind of looks like a straight line, right? But all in all, it's not doing a very good job. And so what we do is we do a residual plot, and now we've got the residual on the y-axis and the explanatory still on the x-axis. there's going to be a line at 0. So this is at 0. I'll scoot this residual note. Oh, just want to move it there. There's going to be a line at 0. Why is it at 0? Well, because the line, we're trying to minimize the distance, right? And so if the line is doing a good job, then the distance should be 0, right? If it's capturing those points. And so it should be centered on 0 for the residuals, right? And so this is so on the left, we've got a scatter plot. And on the right, we've got a residual plot. The residual plot, right, would magnify that relationship that we saw in the scatter plot. So it would make it look something like, well, here, right? We probably saw that in our scatter plot, but with the residual plot, it becomes more obvious, right? So it's magnified. Okay. Any questions about that? No? All right. So let's talk a little bit about correlation then. Because we've talked about all this theory and all this fun stuff. Oh, this is how the line is built, blah, blah, blah. But at the end of the day, I'm going to show you how to calculate the slope and the intercept. And then these will just be kind of thinking more on it questions, right? And so, but just knowing where it's coming from and how it behaves is really good. So, like I said, when we describe a scatter plot, right, we have to talk about the shape or the form, right? Linear versus nonlinear, we have to talk about the strength, and we have to talk about the direction of it. And so we've got a numerical measure for the direction and the strength of a linear relationship, and that is the correlation. So the correlation, and you've probably, you know, used the word correlation. We have this idea, we understand what correlation is, right? That there's this relationship between two things, they're correlated, right? They move together in one direction or another. But correlation is a numerical measure, oops, a numerical measure of the strength and direction of a linear relationship. Has to be linear. Okay. So that's important. And that's kind of a classic, you know, multiple choice, read carefully, right? Because if you've got a nonlinear relationship, the correlation doesn't tell you anything, right? It's not important. And so the correlation only applies to linear relationships. And so the correlation is denoted by R, by a lowercase r or a capital R if you prefer. Here's the pickle. I like lowercase r. The textbook overall uses uppercase R. So sometimes the case matters, sometimes it doesn't. In this case, it doesn't, right? And so R or capital R, it doesn't matter. And the correlation is going to be a number between -1 and +1. Okay? And so is denoted by R or R and is a number It is a numerical measure after all, so it is a number between -1 and 1. Okay. If it's a negative number, you have a negative relationship. If it's a positive number, you have a positive relationship, right? So that takes care of the direction. The strength is, so if you have a correlation of 0, then it's a very weak, it's the weakest relationship that you could have, right? And then as your correlation moves out towards +1 or -1, right? We could have strong relationships in the negative direction or in the positive direction, right? So it behaves the same way as we move away from 0, right? And so as we move closer and closer to 1, we get a stronger and stronger relationship. And so what I said was, well, if we look at something, if we see a pattern, we're going to call it strong or moderately strong, right? And so for number cutoffs, I cut it off at, okay, between -0.5 and 0.5, I'm going to call it weak. Any correlation beyond 0.5 in the positive or the negative direction, I'm going to call it strong, right? You can add your own, moderately weak, very strong, whatever you want to do. But I'm just going to go for strong or weak. Right? You'll be tempted, I know it. And again, this is one of those like field-specific things. For some reason, psychology, they just love to drill down to like the finest levels. I think they have like 8 measures of strength instead of just weak and strong where we have 2. So they really get down to it. So for me, if we're centered on 0, oh, should probably center that, hey? I don't know, whatever. I've got a number line between -1 and 1 here, right? I'm saying roughly at -0.5 and roughly at 0.5. Of course, we can kind of use our judgment and argue either way. But for this portion here, between -1 and 0, I have a negative relationship. Negative relationship. Between 0 and 1, of course, I have a positive relationship. Roughly between -0.5 and 0.5, right? Starting at 0 and moving out, anything sort of within those bounds, right? I'm calling a weak relationship. Anything beyond that point, though, I'm going to label as strong and strong. You can have a strong negative relationship or a strong positive relationship. Nice. Okay. On your formula sheet, and I know I'm running you ragged today, but I've still got time. I know. We can do it. The correlation is on your formula sheet. Looks okay. Don't look at the covariance for now, right? If you're looking at your formula sheet, the covariance is the top one. It's giving you 2 different formulas for the covariance. We're just going to ignore it for now until we get to the correlation, which, so here, we can compute the correlation by saying that the correlation is S sub xy. And we'll break this down, right? But for now, let's write it out over S sub x, S sub y. remember a lowercase s is the standard deviation, right? And so here, this is the standard deviation of x times y, right? The covariance. So we will have to calculate it, but I just wanted to get you guys into the correlation first. If you're thinking about your scatter plot, right, now we're looking at the relationship between an x variable and a y variable. Each of those, we can calculate the mean of x, the standard deviation of x. We can calculate the mean of y, the standard deviation of y, right? So we can calculate all these things. And so S sub x is just the standard deviation of the x variable. So it's the standard deviation of x. At the beginning of, or sort of the beginning of chapter 2, we looked at finding the standard deviation for a small data set, right? And S sub y, same deal, is the standard deviation of y. Like I said, on your formula sheet, there's 2 formulas for SXY. So now let's tackle the covariance. So we need to find the covariance, which is your SXY. Focus on the second formula because it's going to be the one that matches the one that we used for the standard deviation, the closest. And so SXY is going to be the sum of xi times yi minus n times x bar y bar all over n minus 1. The only thing that's really kind of different on here that we haven't seen before, we've seen n, right? N is your sample size. We've seen x bar, that's the average of your x's. Y bar is the average of your y's, right? So we've seen all these before. Not in the same formula, right? But here they are. The only new thing is the sum of the xy's. So what that means is you're going to have to make a new column, right? Just like we did when we found the standard deviation. We found all our x's, and then we made a new column of each of the x's squared, and then we added them up. Now we need to add another column where we've multiplied x times y for each of these observations, right? So now we've got a new column of x times y, and then to get the sum of the x times y's, we just add that column up, right? And so the sum of the x times y, the sum of xi yi, I'll do an arrow because it's not really equal to, I'm just explaining what it is, right? So in your spreadsheet, make a new column, and whether that spreadsheet is on your piece of paper, right, or actually in a spreadsheet, that doesn't matter. But in your spreadsheet, make a new column where you multiply the values of x and y for each observation. Then add them up to get the sum of the xi, yi's. Those subscript i's, you can kind of ignore them or just kind of fuzz them out in your mind. They're not doing anything. They're just saying, oh, do this for every observation. So, all right. Any questions? What was that? Am I awake? All right. So we'll finish regression next day. I'll actually show you how to find the slope and the intercept. But until then, see you on Friday in the lab.